All right. Well, hello everyone. Welcome to the Robotics Colloquium. We meet every Friday, and we're super excited to have Kay speak today. Kay's a PhD student at the University of Washington. I wonder where that place is. Um, and is co-advised by Abhishek Gupta and me. So Kay joined the lab right when I moved to UW in 2017. So she's one of the founding members of the Personal Robotics Lab Seattle edition. And so it's been really great working with her. I think what I've really enjoyed about Kay is she came in as a very strong theorist and a fantastic programmer. We wrote a bunch of theory papers together, and then after that she said, I want to build a robot. And I said, sure, what robot should we build? And she said, I like chopsticks, and that seems hard. And so I told her that we'll spend the next 4 years building a robot that can manipulate with chopsticks, because why not? And I think what's most revealing for me, in addition to all the cool science and research that you'll see, is Kay is a fantastic roboticist and a really full stack roboticist. Spends a lot of time thinking very carefully about building good systems also. There was a time during COVID when she dismantled the entire robotics assembly and took it to her garage and set it up at home and set up a schedule for all of our undergrads to come and do experiments at her home. And there's also a story of when that entire setup was stolen and Kay had to rebuild it from scratch all over again, including, I think, flying to Pittsburgh to get some parts for it. So I think, obviously you would hear about all of that, but I'm sure you all know how hard it is to get a robot to do anything, particularly at 1x. Actually, some of these videos have to be slowed down so that you can see them. So I'm super excited to hear Kay speak. One other thing I'd say is that Kay is workshopping this talk for her faculty talk. So she's going to be interviewing at a few universities for her faculty position. So your feedback is truly invaluable. So at the end of this talk or during this talk, maybe at the end of the talk, please give her send her some feedback. Thank you. So without that, take it away.
Okay. Thanks for the intro, Sid, and also thank you for introducing me to robotics. And nice to meet you all, people. I'm Kay, and today I'd like to take us on a journey to focus on robotics with fine motor skills. So in today's talk, we'll look at a lot of manipulation problems. So naturally, we'll see a lot of pick and place. But we are not going to look at manipulating these large boxes. We're actually going to zoom in. See this cookies? So this cookie is much smaller than the box, and it would require much more delicate motion to manipulate. But we want to further zoom in. So we focus on a particular challenge, a fine manipulation challenge that requires some millimeter precision. So this domain of task is prevalent in daily lives, in industrial setting, assembly, manufacture, and in medical field. So broadly, we would like to use this group of tasks as testbed to work on the frontier of research to solve challenging problems. The truth is, for fine manipulation challenge, there are great working solutions already in factories. So currently, many robots are performing fine manipulation in factory settings. So here are examples of 55 robots putting together a Swiss watch that contains 51 parts. So existing solutions are great, but given the success in these existing solutions, can we transfer it to a different scenarios is the problem we're interested in. So say that we want to manipulate, so we have this working examples of manipulation solution for making watches. What if we want to transfer success to building a sushi? So following the current solution, we will hire some engineers, maybe someone with degrees, maybe they will study the task, and they will design structures to make this task feasible. Some of the structures we can borrow from existing solutions. We can build specific tooling, we can build custom supporting materials, or to align and position each piece precisely. And in this controlled environments, existing solutions would work like wonder. But what if we cannot control the environment? What if I would just want to make sushi in my kitchen, I don't want to turn it into a factory? What if in a surgical scenario? What if we want to work on this patient's heart? Can I really build an alignment pillar inside someone's stomach to reshape and resize the heart so that it lines precisely with my operation procedure? So despite that, the point is, despite that we can add an incredible amount of structure to the environment, there will still be features that will be hard to constrain. And that is the kind of problem we're interested in. Our goal is to develop general systems that can handle a diverse set of tasks, but also working in an uncontrolled, wild environment, like this cooking robot. It's an imaginary AI-generated picture in a human home. So what's preventing us from having this? Well, the complications, the challenge are really twofold. So we have great existing solutions, but to transfer their success to new problems can be challenging. And we also have great works that's trying to build general robotic systems, but they may not have delivered the precision, the fine manipulation that's required yet. So that's the goal of the talk today. We want to set on a journey to empower general purpose robots to solve and automate challenging tasks that require fine motor skills. And we would like to doing so while reducing human burden, while we remove part of this constraint of adding control to the environment. And we're motivated to build a general system using data-driven approaches. So to give you a concrete example, I will use a hard task as my North Star problem so we can think about the challenges. So here, we're going to pick up a coin from a pile of coins. And it is challenging because the motion really has similar precision of error. And if we grab the point, and want to insert it into a hole again, we cannot just wiggle through this. Like there won't be room for error of even 1 millimeter. We have to be very precise in this sort of manipulation tasks. Now, this demo is a teleoperation demo. So what we're interested in, how can we automate this? So in today's talk, I'll share a few contributions I made grouped into 3 directions: hardware, learning from demonstration data to follow the demonstration, and also learning beyond a given set of data. So in the first part, we will build a hardware platform as a general testbed for fine manipulation. We will create an accessible hardware testbed by assembling off-shelf actuators, and we will contribute a human study to learn human strategies. With the data collected, we will then learn to follow human demonstrations. So for example, if we have demonstrations of picking up a small ball, can we teach the robot to do it? So this is a preview of an imitation learning system we developed. By learning from expert demonstrations, robot can grasp a small ball with success rate actually on par with proficient human expert. But that's not the end of story. We can imitate from data set, but we're also interested in, on top of that, going beyond a data set. Because in tasks so challenging like fine manipulation, humans may have difficulty with the task. We may have limited data or low quality data. To overcome this limitation of data set, we will develop adaptive system that can learn from trial and error to develop their own strategies. So that's a preview of the talk today. We'll begin the journey. To push the boundaries of fine manipulation, we'll first build a testbed. So I'll focus on one of my work that's contributing a hardware testbed and a human study. So we purchased some general purpose robot actuators from Heavy Robotics. With some 3D printed materials, we now have a way to build a general hardware stack. We put a pair of chopsticks as its end effector, and you might wonder, why chopsticks? So chopsticks are an example of general purpose fine manipulator. The shape of chopsticks are actually pretty representative of the tone-shaped gripper, which has wide adoption in fine manipulation fields like surgery. Look at all the surgery tools. They look like a tweezer, a tone, just like chopsticks. And humans have demonstrated versatile usage with chopsticks. They can pick up a variety of objects with textures, sizes, frictions, deformability. To show you a wild example, so one crazily dexterous human beings can even use chopsticks to pickpocketing cell phones. So inspired by the human success with fine manipulation, we created a teleoperation interface. So we command the robot here to follow this leader chopsticks held in the human's hand. we can see that this teleoperation interface could achieve great success with human acting as an operator. It can succeed in picking up this tiny balls. So we can also validate the capability of the hardware through testing it on different tasks. We see the system is able to pick up deformable napkins, super tiny beans, a clustered bowl of beans, or a clustered pile of forks. But to do this task autonomously, there are many challenges. So to achieve this level of precision required, I will talk about two of these challenges that's commonly faced when we're using a general purpose robots for fine manipulation purpose. So first, kinematic challenge. So our robot was assembled from off-shelf actuators. These actuators, unfortunately, general purpose, are not designed for fine manipulation. So inside each joint, there are many gears to move each other to actuate robots. But in order for the gears to move and to avoid jamming, there will be a gap between the gears. So that's creating what's called backlash. And if we have a gear-based actuator, it's very common to have this backlash. And the factory would tell us that for this actuator, the backlash is 0.25 degree, which doesn't sound like a big number. But what's going on is if we accumulate this backlash, which is intuitively speaking, this small inaccuracy when we have a positional reading, and we accumulate inaccuracy along the robot manipulator joints at the tip of our robot, we got up to 5 millimeter error. So imagining we're manipulating this tiny coin, but we can be off by 5 millimeter of error. And that is one of the challenge that prevents us from having precise model of the robots. And another challenge on top of the kinematic one is dynamics modeling. So when we want to build a dynamics model to incorporate physics of our environment, of our world, there are great off-shelf physical simulator that allowed us to simulate many of the real-world physics. But to achieve the level of precision we want here, it's still pretty hard. So what's happening here is that we took one of the off-shelf simulator, MuJoCo, and we run some system identification, trying to understand the physical parameter of the world and put it in the simulator. At the end of the day, we record a success trajectory in the real world, and we replay it in the simulator. But we still see a mismatch. So what is happening in the simulator is like the robot seems to just miss it by a tiny bit. So this mismatch is highlighting that we still have a sim to real gap when we attempt to model a fine manipulation problem using simulator. So these are common difficulties that makes it challenge to control the robot precisely. And we're sensitive to these errors of like 5 millimeter, 1 millimeter, because our tasks are sensitive. Point is that what's normally accessible when you manipulate a coarse like tabletop objects, it soon become catastrophic if you scale down and look at something much more finer. Let's take a step back. Let's think about humans. Humans have demonstrated great level of control in fine manipulation. Perhaps they can control our general purpose hardware to do the task. So that inspired us to conduct a user study. We hired 30 subjects at university campus. Despite that, each user only spent 10 minutes with this robot teleoperation interface. We witnessed some impressive success. So this fine manipulation challenge at hand, it seems like humans don't necessarily need to build a precise model of the world to understand exactly how physics work. They're good at it, they do it. So this teleoperation success convinced us that we can collect some data. So that concludes our first part of the talk. We have built an accessible testbed. We ran into some common challenges for precise modeling and control of general purpose hardware. We witnessed impressive success with human teleoperator, and we can collect data. So naturally, we run into the next step. We'll learn from the demonstrations we need. So look at the teleoperation interface. There is our robot trying to match whatever is a human leader's pose. So to put into the context of learning from demonstration, we will denote the robot pose as the state, and we will denote the human action as labels. So if we want to learn from human demonstration, we want to run a robot policy that can map from an input state to a distribution of actions. And the truth is, there are many imitation learning algorithms to do so. There's behavior cloning, the timeless classic one that just needs data. There is Dagger, a very practical one in drone flying that has great results. There are GALE, generative adversarial imitation learning, that has shown very fantastic results in simulator. And there are so many of them, and we want to understand like what it actually means to learn from demonstration, and what is the difference actually between these algorithms. So I will focus on one of my work that tries to unify imitation learning algorithms into one framework. So one of the challenge in imitation learning can be multimodality in data. So for example, we can drive a car around an obstacle by going left or right. There are two modes, but both are valid. If we attempt to use the simplest form of imitation learning, behavior cloning, to learn this behavior, we might see the learner ended up hitting the obstacle head-on, even though this crashing behavior is not in our demonstration. So others have validated similar phenomenon in learning multimodal expert data. So what is going on? Why are we doing something that the expert was not demonstrating? So we posit that what imitation learning is really trying to do is distribution matching. So following common notations will have a learner policy that, given the state, do some action, and we'll have an expert policy pi star that also maps state to action. We can run any policy to collect trajectories, and if we run a policy many times, we can have even a distribution of trajectories. Now we posit that imitation learning is really trying to minimize the divergence between the trajectory distribution of the learner and expert. So if this is our objective, then two questions would arise. So how do we measure this divergence, and how would we optimize it? So one of the divergence, there are many of divergence out there, but one of them that we can use would be KL divergence. So if we choose to measure divergence using the KL divergence, it turns out that we can plug it into our objective and simplify it, and we ended up recovering behavior cloning. So now this established the connection between KL divergence and behavior cloning. How does that, what does that mean? Like what does it tell us about behavior cloning? So the choice of minimizing KL divergence means that behavior cloning would maximize the probability of the expert action along and only along the expert trajectories. So if there's multimodality in the data, like shown here in the gray area, there are two modes to the expert. If we run behavior cloning with a unimodal Gaussian, we got this green policy. It will actually hit obstacle head-on because to the optimizer, it's trying to cover all the modes. And it is doing something that the expert does on expert states. What this objective failed to consider is to prevent the learner from doing something that expert does not do. So that is a fundamental drawback of running behavior cloning. It cannot consider places outside of expert demonstration. So can we fix that? What if we just change the objective function? What if we choose a different divergence function? So KL divergence does mode covering. What if we choose reverse KL divergence, which focuses on mode seeking? So can we just plug it in? Now, if we plug in the reverse KL divergence into our objective function, it turns out that we get something that's intractable. This new objective function needs us to know the expert policy. So if we want to run it with an expert policy sitting there, great. But oftentimes, we are trying to learn expert policy from expert data, not from expert policy directly. Otherwise, we can just copy it. So is there any way for us to optimize this new objective using our KL divergence? So we find that KL divergence and RKL divergence, they all belong to this family of F divergence. A very cool tool that comes with F divergence is that they have this convex conjugate. So by definition, we can rewrite an F divergence into its variational representation. And now with this new definition, we can plug it into the objective function. So using Jensen inequality, we will ended up having this new objective that we can estimate using just samples. Remember, the old objective requires us to know something that's intractable, but the new objective we can optimize using just samples. So generalized from this estimator, we can actually create new algorithms, for example, for reverse KL. We can also recover some of the state-of-the-art imitation learning algorithms just by choosing different divergence. So this framework allowed us to formalize a few state-of-the-art imitation learning algorithms into one framework and help us understand their characteristics by the choice of divergence. So it gives us insight into improving algorithms like behavior cloning, who is very popular right now, but can suffer from multimodality issues. So right now, behavior cloning, the simplest form of imitation learning, is gaining a lot of adoption because of the simple assumption. It only needs us to have expert data. This allowed it to be scaled up. Like if we have a large quantity of data and that's the only thing we have, why don't we try behavior cloning? But as we already showed, there's no free lunch in the world. Behavior cloning can potentially suffer from multimodality issue. And here we'd like to point out another difficulty of running behavior cloning, which is compounding errors. So the more technical term of it can be distributional shift. And I would like to introduce you to distributional shift. So distributional shift is like taking an exam. So say that I did some study on math problems. I have low validation error. I have low training error. I do great on math problems. But I walk in the test room. I got tested on English, which I didn't study for. So I did poorly on the English one test time. I got thrown the question. So basically, distributional shift means that I cannot take a test that I didn't study for. So you might wonder, why are we doing this? Like, why at test time I'm given something I didn't study for? So the truth is that there are many reasons that contribute to this compounding error issue that push the agent astray from the training data. So I will highlight two reasons that are relevant for fine manipulation. So remember the hardware noises we talk about? So many robot actuators could make noise. Part of them could come from the backlash we talked about earlier. So this noise can accumulate as times go by, as robots keep rolling out a trajectory, and eventually they can lead the agent astray from the training data support. And another aspect that contributes to distributional shift is the data scarcity issue. So remember, it would be nice if we have like a wide internet scale of data, but right now in fine manipulation, task is so hard, we have a limited set of data to work with. So we have a limited test question bank, and we're trying to study all the problems that's out there in the world. So we have very poor guarantee on how we will do at test time. So I'll talk about two works that I contributed to mitigate the compounding errors issue. So if we take a closer look at the compounding errors, what's happening here is that we kind of start making some mistakes even early on. And the errors would accumulate, and we got pushed to some auto-distributional states that we're really clueless about. But what if we generate some corrective labels that help us stay within the expert support? So if we're always in the place where expert has told us what to do, we'll be good. We'll just stay in the comfort zone. But how can we do so? So previously, people has leveraged, like by adding more assumption, for example, an interactive expert, people have showed that if I can have an expert that constantly give me new label, I can just get more and more data on more and more state space. I can have a great coverage of everything I would encounter at test time. Then I would solve the problem. But we just said that.
Just a quick clarification that like the expert might not tell you to come back to the data. The expert can tell you something else.
Yes. So a small clarification here is that we say that we want to generate corrective labels because we want to stay within expert support. And this previous work that leveraged an interactive expert, they could use expert to give optimal label on more state space. So they increase data support effectively. Now, we really don't want to bother an expert, because if you just drag me to a room and ask me, okay, what's optimal solution? Like, what's optimal label right now, if this is my state space? I'm going to be very confused, like, what should I label this? So in manipulation problem, it's actually pretty counterintuitive, even for humans who are great at the task, to give you an optimal label for a randomly sampled state query. So we want to reduce human burden. We want to not bother an expert. And what can we do to generate this corrective label? Something that can be useful is if we know the dynamics model of the world. So let's run a thought experiment. So if we know the dynamics of the world, maybe I can then sample some random starting place in this room, and I'll just keep querying my dynamics model. I will not stop until I figure out a path back onto my expert support. There are many ways to do so already. Some of them were noticeable one, including the offline reinforcement learning works. But what if I'm so lazy that I don't even want to assume knowledge to the dynamics model? I want to keep minimum assumptions so that people can just scale my method up with data. I don't want to add an assumption that we have to know the dynamics. So one quick intuition is, what if we use a dynamics model that is learned from the data? So we only assume access to the data, and we will learn the model, and we'll use a model to generate some labels. And that is the framework we propose. We call it a continuity-based data augmentation framework. So the caveat in using a learned model is that, can we really trust the learned model? We just have a whole inspection about if you train anything, it will only work on data support. So a learned model cannot be trusted if you just ask it a random state action space that's outside of its own data support. And the key insight we have is that, what if we can identify some structure of dynamics that would allow us to trust a learned dynamics model in some space that's in approximate to the data but not exactly there? So what can we do here effectively is that there is a structure of local Lipschitz continuity that's been very popular in the classic control literature, that's been widely adopted, give birth to linear quadratic regulator, and that has been underexplored by robotics learning community. What if we use this structure? With this structure, we can bound the errors of the dynamics model at state action space that's close to the data support. So it's very intuitive that if this structure is true, we will just search for labels within a bounded area. So very concretely, previously we've said that if we have a true dynamics model, we can just plug in the dynamics model, do a lot of sampling query until we find a way to go back to expert support. And now with a learned dynamics, what we will do is that we'll still query the model, and we will only trust the model if the result is stayed close to the data support. So to show you an example, we visualize the generated labels on a toy problem, Pendulum. Here, I plot one of this expert rollout from Pendulum. You can see that the pendulum is going to swing, and we try to stabilize it in the center around here. And if we plug in our proposed algorithms, we'll generate this green dots. That's our generated states, and we'll generate this arrows, the green labels. What this trying to show you is a visualized way to understand what are we generating. So we are generating some state that's close to the expert demonstration, some action that's also similar to the expert had done in the proximity region. And it's going to point us back to expert support. And a great advantage of doing so is that if there is local Lipschitz continuity and we can indeed capture it, we can derive theoretical guarantees on the quality of labels. So unlike some of the existing work that learn a model and trust the model over a broad state action space, we trust our model in a limited state space, which give us theoretical guarantees. So how does this look on the real robot? So we tried it on the Lego insertion task inspired by pack insertion, and it's through assembly. So what's happening here is that we're trying to put these little pieces into one of the hole on this Lego structure, and if it's actually plugged in properly, this little windmill is going to spin. So we have seen on this task that behavioral cloning could be missing the insertion point by just a few millimeters, but then it's a wrong point, and then it's going to have current shift problem and then drift out. And in contrast, we have shown some success with our method that successfully inserted the piece to the correct spot. Now, in developing these algorithms, we also explored the possibility of applying it beyond our fine manipulation domain. We tried on different domains like drone flying and car driving to ensure it's a general algorithm. What's interesting is that we also identified a special case of our algorithms. So in another work, Grasping with Chopsticks, we identified a special case that allows us to not train a model at all to generate corrective labels. When we use certain controllers, like position controller, they have invariance. We can inject some noise to the state space and use the same positional command. This allowed us to almost like generate labels for free, and we tried it on our fine manipulation domain. And it worked pretty awesome. On the left, we show the baseline behavior cloning. It struggles to pick up the small ball. Notice that it's a close miss, but this is a failure by our evaluation metrics. And on the right, we show our own agent. It greatly improves the success rate of the baseline. In fact, it was able to match human expert success rate. So that concludes the second section of my talk. We have presented a framework for unified imitation learning. We have proposed 2 algorithms to combat the compounding errors in imitation learning. And shall we just use imitation learning for everything? Shall we just go out there and collect a massive scale of internet data and we solve all the problem out there? So if we go along that line, we tried it a little bit. We want to do that, but we realize that many of the tasks we're doing right now are hard tasks. So on these hard tasks, humans may have trouble completing them. The twist is here. Like this kind of hard task is exactly what I want to automate to help humans, to augment their dexterity, but also exactly where humans are having trouble right now. So we have limited data availability. So if we choose to leverage data-driven approaches for hard tasks, I think it's relatively infeasible right now to say that we have abandoned high-quality data set to work with. So we have to be able to do something else. So a further complication is that in many of the tasks that we're considering right now, it has many variants in the initial condition. One easy way to visualize is dynamic condition. So this ball can be it's moving in a limited region, but it can have different velocity. It can have a different momentum. And in the kitchen task on the left, like if we're going to grasp this little floating pieces of eggshell, it's going to move around because we might fail. And then every time we tried and failed and moved it around, it's a new condition. It would be hard to collect a data set with expert optimal demonstration over all variants of these tasks. And what should we do? We go back to our human study. How are humans so effective on these tasks? How are they so effective even when conditions are changing? We realize that the key to human success is actually in their adaptation. So this is what it looks like when we just sit a human down and ask them to try using our platform to solve this hard fine grasping challenge. So the empirical success rate would be relatively low on the most difficult object here, the ball, because it's very hard to grasp a slippery ball using chopsticks. But just need one trick, we can boost the human success rate, which is to allow them to retry. So if we allow humans to retry, to reattempt, within 20 seconds, the success rate got boosted, even on the hardest task, from 26% to 80%. That's more than 3 times boost. The boost is more significant than any of the reinforcement learning or imitation learning work I have done so far. So humans' key of success is to adapt to whatever failure, whatever mess they have made. They're just going to keep retrying. And that inspired us that we want to develop adaptive solutions, just like humans, that can work on scenarios outside of the fixed given set of data that can do trial and error to improve itself and succeed. So under this setting, reinforcement learning is a promising paradigm. It enables the agent to continually improve itself by conducting trial and errors in the environment. But the twist of running reinforcement learning is that even though there are great success out there, they haven't delivered the precision we want. We don't really know if reinforcement learning is suitable for a manipulation task as precise as what we want to do. And that raises 2 further questions. So in imitation learning, we talk about like we want to collect a lot of data. In reinforcement learning, the question still persists. How much trials and errors would reinforcement learning need to succeed? There are no reference point, unfortunately, for the precision we consider. Like, it would be nice if someone can tell us that, hey, given this tabletop manipulation, you just need 2 hours of data. That would be awesome. But for precision task, there's no real reference point or benchmark to think about. And further, if we're going to deploy a real-world reinforcement learning algorithm, every time when the RL baby is learning, we, the human, got to work in there and reset to ensure that it's in the right initial condition to start learning. So if they're collecting 200 samples, that means I got to work in 200 times to do that. That can be pretty annoying. So we took on a journey to explore, like, can we build a reinforcement learning system in real for fine manipulation challenge? And this is the result. We contributed a system, CherryBot. It uses about 30 minutes of real-world data for reinforcement learning on fine manipulation. It can succeed even with human disturbance. It can plug a moving cherry in the air with wind blowing at the cherry and shakes it. So if we look at the slow motion of this video, so how the robot is doing the task is that it's actually rapidly attempting at the task. It might fail, see here, but it's able to fastly adapt to the resulting condition, adjusting the grip to recover from the failed attempt. And that's what allowed our system to achieve very good success rate on this dynamic fine manipulation challenge. So the key to our system is actually to leverage prior information that's accessible on many robotic hardware. So what do I mean by prior information is that even though we say that it will be hard to have accurate simulator, we might have an approximate simulator. It's relatively easy to build an approximate simulator from zero, from scratch to 50%. And similarly, we can have demonstrations that might be suboptimal, but they tell us about the physical world, about the task. We might have some off-shelf state estimation modular, so we don't need to start from like pixel level, like perception challenge. So if we put all this system together, we ask, can we put all this imperfect information together and then push a system to solve fine manipulation challenge by making learning more efficient? And I'm going to focus on one of my work on reinforcement learning here that propose a practical training paradigm to combine all the private information. So our training paradigm will combine accessible private information from these three categories, and it will conduct 3 steps of training. So it will first pre-training a simulator, and then fine-tune in the real world, but in a lab, in a controlled setting, and third, deploy it in the real world. So the first step is to pre-train an agent in our approximate simulation. Because of the sim-to-real gap, we have to follow some of the conventions to randomize the dynamic parameters in the simulator so that our agent is robust to varying dynamics. And in this process, we have to run certain ablations to determine which parameters is suitable for fine manipulation tasks. But after that, we also want to boost the reinforcement learning efficiency in the simulator. We find that it's very effective, actually, to include demonstrations in the replay buffer whenever we train reinforcement learning agent. Say that we have written some heuristic controller to attempt at the task, and the heuristic controller can only work in a static scenario in limited condition. It has less than perfect success rate, but we can use it to collect data. There's nothing wrong of using a suboptimal data in reinforcement learning training, and we have validated that that can greatly boost the learning efficiency and then enable the agent to succeed in many cases. So pre-training in the simulator will give us this successful agent that works in the simulator. And naturally, with the successful agent, let's deploy it in the real world. Because of the sim-to-real gap, on the right, I show you what it looks like. And these are exactly the same policy that we put from simulator to real world. And this is doing something that I don't even know how to interpret. It is not working yet. And this comes our second stage. We want to fine-tune this agent. So one technique we emphasize during real-world reinforcement learning fine-tuning is a synchronized update. So in simulation, in classic convention, when we train reinforcement learning, we interact with the environment simulator. So we will collect a data from the simulator, and then we do some update of our function approximator. But in the real world, this collecting data, it really takes time because there's a physical meaning behind it. So we propose that we should separate these 2 threads. So there's the robot, it's going to collect data, and it's probably going to be blocked by that step because it takes time to collect that data. And behind the scene, we can have a compute that actually does all the learning update. So this message is not new. Like there's previous work that proposed doing so, but their emphasis was more on leveraging big compute. But here, in our case, we only have limited compute, but still it makes sense to do it because robot collecting data costs physical time, and we're interested in not only optimizing sample efficiency, but also real clock time efficiency. Now, this synchronized update allows our agent to conduct more updates per data point it collected and actually boost the training efficiency in the real world by 3 times. So this boost in the real world actually is slightly bigger empirically than what it boosts in simulator even. And another thing that we consider when we fine-tune reinforcement learning is to set up this proxy task. So because I don't want to go in and then reset the robot every time it's training, we develop a cute trick that we hang up a ball by a string, let the ball swing with stochastic velocity and ask the agent to grasp it. So effectively, the task has a lot of stochasticity because we don't control the ball's swing velocity or motion anymore, and we just let RL agent deal with it. It simplified our burden to reset the thing, but it also kind of makes the task slightly harder. And our insight here is that we can use our control of the environment at training time. We can actually make it train on like a task A, and later on we will show you how to deploy it on different scenario in the slight variation of the task. So now we have a successful agent. It's pretty good at grasping this ball swing in the air, but can we actually use the system to do fine manipulation challenge? So we try to deploy our system in novel dynamic scene for fine grasping across different objects and environments. We would use off-shelf state estimation, and we would throw novel objects at our system to test its ability to generalize. We see some decent performance. My personal favorite of this video is the top one. This is a very slippery glass ball, and it can be moving, and this is the task that I would say that my robot finally does something better than I do. Now, our system has about 64% success rate in this array of tasks we show here. It's a pretty diverse scenario. We can further deploy it with different perception modular in more complex scenes. So here's some examples of running our system with different off-shelf detectors, more complex food manipulation scenarios. And one interesting thing we would like to point out about running with an external perception modular is that the perception modular might have noise. So for example, if you have used YOLO, the famous fast, great regression-based visual detection modular, you know that it might have some tracking error. So tracking error can have a static part of bias or a dynamic part of noises. So we focus on the noises part. So if I have a static scene here, and I'm going to detect the cherry here, I'm going to get a bunch of different estimations. The blue box or green box, they are slightly off by a little bit, but they are all pointing to the cherry. And if we're doing this task, which requires super precise grasp, and we don't have a precise estimation of where cherry is, we need robustness of the learned policy. The policy needs to keep retrying. The policy needs to be able to handle this noise in deployment time. So here we highlight that part of our training design allowed our agent to demonstrate robustness through its own trial and error, even though this adjustment behavior was not in the demonstration data. So finally, to convince you that we built a cherry-picking reinforcement learning system, but we didn't cherry-pick the reinforcement learning system, we tried it on 3 different random seeds and then observed that with similar sample efficiency, about 2 to 3 hours of real-world training, it can solve the task. So that concludes the third section. So we were inspired to teach the robots to learn beyond a given data set so that it can surpass the limitation in our data set. We propose a training paradigm to make use of practical information like simulator, like suboptimal demonstration, like off-shelf detectors to boost learning efficiency. There's a recurring theme or insights or lessons I learned from my past work. Even though we said that we want to empower general purpose robot hardware to do fine manipulation challenge, and we want to use data-driven methods, data is not everything right now. We find that if we can leverage structures or prior informations in the problem, we can greatly boost the learning efficiency of data-driven methods. So we have seen it in my learning from demonstration work where we leverage a physical structure or local Lipschitz continuity to generate corrective labels, and also in this learning beyond dataset reinforcement learning work where leveraging all the prior information, doing pre-train, doing fine-tuning, doing it in a controlled setting allowed us to have great sample efficiency. So that is a very interesting future work direction I would like to explore more. So in the realm of data-driven learning, nowadays, probably this year, we often find ourselves asking, would data solve everything? If something is not working, should I just collect more data to cover all variants of the state space I'm curious about, and also cover all the recovering action that I want my learner to be able to show. So my intuition, my take on the question is that no, I believe that robotics learning is bounded not only by data, but also by structures. So to give some kudos to the data-driven research, I think it's a great time right now that more data become more available, and we would know what more data would enable us to do. But I think even with, because at the end of the day, we have a finite sample of data. It might be a huge number, but that's a finite set. So to think about what this data is trying to tell us, I would like to point out a difference between a language domain and our robotics domain. So in language domain, we have seen great success achieved by ChatGPT by using large scale of data. But in language domain, all the conventions are constructed all the structures are constructed by convention. So I can start gibbering some random thing, and I can call that case language number 1. And if I gibber enough, I will be able to probably fit some statistical model to learn the structure in that gibberish language I made up, because structure in language is conventionally constructed. But in robotics, we have to operate in the physical world. Therefore, we have to abide by the physical law, for example. So I believe that there's an objective part of the structure that's not constructed by convention that we can capture and study. And if we can do so, like I've shown a little bit in my preliminary work, if we can do so, we'll be able to boost the learning efficiency of data-driven method. So there's some other exciting research going on in the community that tries to, for example, leverage simulator to get a diverse exploration strategy that can hopefully boost a data-driven methods in deployment time. There's also great work done at UW that tries to take the existing classic control literature, the MPC method, and blend it with a data-driven method. So I view it as a way to imbue data-driven robotics with structures. So that can be exciting research that I would like to work on and collaborate if any of you are interested. And another direction that I think are cool would be data collection. So in my past research, we have shown some promise in data-driven robotics in the lab. We use imitation learning. We sit down and collect some data. We use reinforcement learning. We set a controlled setting where the robotic can finally collect data for itself without human intervention. But in the long run, if we really intend to scale up data, if we really want to collect more data, I believe that we have to be able to collect data from the user. And it doesn't just mean that we invite Arabs and Turks to come into the lab and sit in our lab setting to collect data. I mean that we want the robot to go to the wild environment. So right now, the criteria for robot to go to a deployment environment is that there's a checklist. Can you do task A? Can you have a safety guarantee? Can you have a robustness guarantee? And if that's satisfied, we will deploy the robots. And we will finally transfer the lab from lab to home setting. But perhaps there can be a paradigm shift. Don't know if this is a way to go, but this is just a food for thought, that perhaps there's a paradigm shift that if we have an interface that showed that it will be able to work on task A given X and Y and Z, we can then deploy that interface into a wild human home, for example, and expect it to interact with the human, collect data, and eventually get the task B and C data. So that is a paradigm I'll be interested in building towards. So as a first step, one immediate direction to research on would be shared autonomy. So we built in our past research a teleoperation interface. It's an example of a very naive shared autonomy system. It helps humans by tremor canceling. So a more fancy, advanced version of this can be the surgical robot teleoperation interface that other people have built with also great precision. But if we want to work on shared autonomy in fine manipulation and really to augment human dexterity from the point of shared autonomy, we have to actually think about what robot can do for human in this case. Like right now, it's just purely relying on human movement. But what if the robot is slightly more clever, like an apprentice? It observes what we do, but it also helps. Many of the existing shared autonomy work right now, if we pose this problem, they would formulate it as a POM-DP. They would assume that we know human intention, or maybe this human intention has a subset of goals, and maybe we have a human model, so we can infer human goal. And then once we know what human wants to do, we can help them do it. But the trick or the twist of doing shared autonomy in fine manipulation is that there's an interesting interplay between human intention and human optimality. So in fine manipulation, when tasks are so hard, humans might have subtle and suboptimal maneuvers. This is where robot can help, but this is also where human data may not be trustworthy. So many shared autonomy work have built things with a clear human model and human intention and update rule, but there are a few works right now that explore how to handle suboptimality of human behaviors, and what if we just don't know human intentions at all. So that is the direction I want to push, to deploy a real-world interface for data collection on fine manipulation challenge that can accommodate human intention being suboptimal. So the goal eventually is to build a fine manipulation system in the wild. Since it can be costly or infeasible to control the environment, we want to accommodate various daily needs of human beings in their nature habitats. And there's a real-world problem behind this, that we have a big population of Asian population, and they're losing dexterity. So I'd like to ask you a question. Do you think right now in the United States, do we have more old people over 65 years old? Or do we have more of children under 18 years old? Make a guess.
Old.
Old people?
Old people.
Okay, let's see. So according to the US Census, in 10 years, will be about the same number of older people and children. But after that, we will have more old people and gradually increasing velocity of more older people. And the truth is, even right now, over the globe, there are about 400 million people older than 65 years old. That's higher than the whole US population, to be honest. So this population is faced many challenges as they age, and one of them is losing manual dexterity. So a driving goal of my research is to match and augment human dexterity. So we can help the aging population by pushing the research frontier to solve the problems that require fine motor skills. So I listed all the works I've done so far for reference. We're still far from getting human level of fine motor skills in all areas, but this lifelong journey has just begun. And I'd like to take a moment to thank to all my collaborators whose help and guidance enabled me to make these few contributions, because I started as someone who doesn't know anything about robotics. And it's with the help and guidance of all these fantastic people that I'm able to learn how to do this and then try to figure out a way to teach my robot to do this. And that concludes my talk. Thank you. So, happy to take questions. Okay.
So when you ask to label action in using a local Lipschitz continuity,
yes.
How do you define the region? Because in your demonstrations, you have a chopsticks, and yes, the action state space is high dimensional, but you don't have constraints as in surgical operations, in which case your robot needs to move in a certain way, which the trajectory is complex, and that if you choose a big local continuity region, you might not, you might mislabel one of the points to the other, and it might cause maybe damage to human organs internal. How would you define the region?
Okay, so great question. Let me recap it. So the question is, how would I define the region of local Lipschitz continuity when I intend to leverage this region to generate corrective labels? I think there are two aspects to answer this. So first is about capturing the local Lipschitz continuity, and second is about optimality of generating corrective labels for the task. So on the first aspect, there's actually the physical aspect to the problem that's outside of our control, that it's a physical system, it have some varying level of local Lipschitz continuity. So empirically, to capture that, we intend to train dynamics model that given the data, because data is the only thing we know, like given the data, we believe that we can train this model, and if the model is fitting on the data, we're going to trust the model's judgment on whether a space is locally Lipschitz. And then we use that learned model in places where it believed to have local continuity to generate labels. And then to the second question, when you say that we could generate a label that actually damage patient's organs, so that's actually a valid concern to this approach. We indeed actually are able to construct adversarial examples where following our algorithms would make us fail the task. The reason is because that corrective label may not be optimal label. So if I, for example, trying to fly from Seattle to New York, and I somehow get distracted and go to Oregon, Portland, the optimal thing to do is probably going from Portland to New York directly. But if I do corrective labels, they're going to come back to Seattle first and then go to New York. So you can see here, this example trying to say that because we don't really know what's going to happen beyond the expert data support, we have indeed very poor guarantee on if this method is going to work for all problems to boost the task performance. What we can find is empirically on some problems, it could help you.
Can I add a comment that, I mean, if you were performing surgery, then you'd probably have to augment an algorithm like behavior cloning with other constraints that you produce, right? Like currently, like the case point is that like, if the expert wiggles a lot, then we assume that the Lipschitz constant is low then. If the expert is very careful and shows many trajectories of being very careful, then we assume that the Lipschitz constant is super tight. That means that we need to be careful. So the Lipschitz constant is estimated exclusively via the data that the expert provides. But you're also absolutely right in that, like, if you only have one trajectory through, like, you know, some part of the organ, then we can only extrapolate from the data that is given. So I would probably like augment methods like this with other like safety techniques that are able to provide these guarantees of not hitting other things.
Thanks. And question?
Yeah, so in your, you showed that like humans get better, you know, if you give them 20 seconds instead of just giving them one try. Do you have a sense of like how much they improve over that time? Like if you look at just the kind of probability of success of individual trials, like how much of that success is just because they get to try again and roll the dice again, and how much of it is because they're actually getting better?
So there are two kinds of improvement that you're saying we might want to consider here. The one is that in one singular trial, if I treat you as a cloud machine and give you one chance of attempt at the task, can you succeed? Versus in the same trial, if it's capped by time, 20 seconds, can you succeed? So the large boost of going from cloud machine style of like one take or no take to 20 seconds and keep retrying is what human boost we observed. But if we allow human to keep attempting at the task, like in this case, so we give humans 3 trials on the same task object, we can see also boost of human success rate. So human learning is really on both levels, I would say. Like one is that they accumulate experience for the same task, and another one is adaptive feature we identified.
I think it's another question there as to like, how much do we attribute it to just stochasticity? Like if the human did the same thing 3 times, and they succeeded the 3rd time, like maybe it's because like it's just stochastic, right? Like just flipping a coin. First time it didn't work, second time it didn't work, 3rd time it worked. Not that they're learning anything at all.
The end goal is to be able to flip the coin and succeed on the first time, despite the potential stochasticity in this process.
So do they fail, and then succeed? So that would mean that they've learned something.
Oh.
But if they just fail, succeed, then I wouldn't know whether they flipped a coin or not.
I think that's a great way of quantify or to go back to our evaluation metrics for success. So we were proposing that instead of a claw machine of fail at the first time and stop you, we encourage you to fail, succeed. And in our own evaluation right now, we conduct a few trials for the robot, but we actually haven't done as much of that for humans to see if they, over time, can succeed more in. So this is so part of the success probably is contributing to this, but we didn't run ablation to isolate that factor. Okay, any other question?
We're out of time. Thank you.
Okay, thank you all for coming.